All right, so welcome everybody to our Quasiworld today. So our first speaker is Jamie Juul, and she will talk about arboreal Galois groups of postcritically finite quadratic polynomials. So please, Jamie.
Okay, well, let's get started. So I'm going to be talking, as you said, about arboreal Galois groups of post-critically finite quadratic polynomials, and I will define all of those things as I go through the talk. This is going to be joint work, or this is all joint work with Rob Benedetto, Dragos Ghioca, and Tom Tucker, and it actually comes from mostly two papers, but a little bit from three separate papers by the same group of authors, and I'll show you the list of papers at the end of the talk. Okay, so first I have a bunch of notation to introduce. Um, so our arboreal Galois groups, I'm going to get to the term arboreal in a minute, but the slide is at least going to introduce the kind of Galois groups that we want to study. For, in this case, just quadratic polynomials. I'm ignoring that word post-critically finite for now. I'm going to let K be any field with just characteristic not equal to 2. So I need to avoid characteristic 2 to make all of this work. And I'm going to fix an algebraic closure, K bar. F is going to be a quadratic polynomial, which, since I'm avoiding characteristic 2, I know I can conjugate to get into the form z squared plus c, where c is an element of our field K. I'll write f to the n to represent the nth iterate of f, and we can define this recursively as f composed with the n minus first iterate of f. I'm going to choose a point x naught in my field. I'll refer to this maybe as a base point. It's going to end up being the root of this tree we'll build on the next slide. And I want to consider the preimages of this x naught under the nth iterate of my map. And I'll denote that f to the minus n of x naught. It will consist of all the elements beta of k bar that get mapped to x naught under this nth iterate of f. I'm going to define now some field extensions so I can start building a Galois group or multiple Galois groups. I'm going to write k sub n or k sub x naught n because this field will depend on x naught, but I'll suppress the notation when it's kind of clear what's going on. And I'm going to do this just by adjoining this nth preimage of x naught to my base field k. This is going to be a Galois extension simply because it's a splitting field of a separable polynomial. So I can think about its Galois group. I know that maybe Galois theory isn't the main interest of a lot of people in this seminar, but remember, Galois group is just the set of automorphisms of my field, and because I built a Galois extension, the number of automorphisms matches up with the degree of the extension that I've built. All of these fields kind of nest inside of each other. So let's see, I've made all of these fields nest inside of each other. I'll have K1 contained in K2 and so on. And so if I just take the union of all of these fields, I'll still get a field, and it will be also Galois over the base field. And so I can consider the Galois group, or group of automorphisms of this infinite extension of K. And I'll denote, let's see, these smaller fields, right, Kn as I showed. The Galois groups of the Kn over K will be called Gn. The infinite extension will be K infinity, and the Galois group will be G infinity. And as I said, I'll decorate this with a little x naught when necessary to clarify what's going on in the problem. Okay. You can think of this infinite Galois extension as just an inverse limit of these, or sorry, this infinite Galois group as just an inverse image of these finite Galois groups, if it feels easier to think about Galois groups as being finite things. So our problem that we want to answer in this whole field is to try to describe these Galois groups in terms of f, x naught, and k. And in this particular talk, we're going to focus just on quadratic polynomials, but you could imagine how I could build this whole theory for rational maps in any degree. Okay, so where does the word arboreal come from? Well, we're going to build a binary tree associated to our backward orbit. Now, I didn't define backward orbit yet, but the backward orbit of x naught is just going to be the union of all of these preimage sets that I defined on the last slide. So I want to build a tree, and the nodes of my tree are going to be the elements of the disjoint union of these preimage sets. And I'm going to put the nth preimage of x naught under my map F as the nth level of my tree. And so what this looks like is x naught goes here at the bottom, and then the second level of my tree would have the preimages of f under the first iterate, or the preimages of x naught under the first iterate of f. So these are just the roots of f of z minus x naught. This is a quadratic map, so there should be two of them. And then I'm going to draw edges in my tree from some gamma to some beta if f maps gamma to beta. So in this case, f maps both of these to x naught, and I would draw out my connections like this. The second level of my tree should have the roots of f squared of x minus x naught. There should be 4 of these because this is a quadratic map. And if my roots at the first level were, say, alpha 1 and alpha 2, I know that this polynomial is going to factor as f of x minus alpha 1 times f of x minus alpha 2. And so the 2 of the nodes at this level will get mapped to alpha 1 under the first iterate of f, and the other 2 will get mapped to alpha 2. And I can keep going, building my infinite tree in this way. Let's see. In this way, I get a binary regular rooted tree as long as I assume that x naught is not in the forward orbit of my critical point. Otherwise, I would have to maybe put the same node twice or something in my tree to make it work. So we're going to ignore that case. So there's my arboreal that we're talking about. Arboreal Galois comes from the fact that these Galois groups we want to study end up being tree automorphisms of this tree. So if I take any element of my absolute Galois group, this is going to induce an automorphism on the tree because remember, the homomorphism of a field is just something that preserves my addition and multiplication. So it's going to commute with my polynomial, any iterate of my polynomial f. And so my Galois group is going to be both level preserving on these nodes, and it's going to kind of maintain the connections in the tree since my automorphism will commute with the polynomial. And so what I get is for each of these Galois groups, G infinity and Gn that I built, an embedding into a set of tree automorphisms. The aught t, the t that I'm writing here is going to refer to kind of the infinite tree. And Tn is going to be kind of the truncated tree, truncated at the nth level. Okay, so now I've transformed my problem from understanding this Galois group that didn't really have any structure to using the fact that I'm taking iterates of the map to get an embedding of my Galois group into the automorphism group of this tree. And I want to mention that kind of any time in this talk when I talk about groups being isomorphic or homomorphisms between groups, I'm always thinking of this as being homomorphisms or isomorphisms between the groups acting on trees. So the homomorphisms will be equivariant with respect to the action on the nodes and the preimages and the nodes of the tree. Okay, to make this maybe a little bit more familiar to some of you, there's a special case of this problem where I think about profinite iterated monodromy groups, but maybe not quite in the context that you're used to. So if I consider K to be some other field, little k, adjoin a transcendental element T, but my polynomial f still is defined over this field little k, and I pick my base point x naught to be my transcendental, then the thing that I get, we call a profinite iterated monodromy group. And the benefit of doing this is we get to break down our arboreal Galois group that we want to study into kind of its separate pieces. So we get this group, which we call G arith, which is just the Galois group, the infinite Galois group with the base point T. And we call that the arithmetic arboreal Galois group for f over k. And it has a subgroup, or the way I've defined it, maybe something isomorphic to a subgroup, which is just the set of elements that fix anything that's algebraic over that field little k. So I can construct that just by maybe taking the compositum of each of these fields k and k infinity with k bar, the algebraic closure, or an algebraic closure of k. When I do this, I can So that group I'm going to call the geometric, sorry, I'm getting out of order, the geometric arboreal Galois group for F over K. And that's going to fit into an exact sequence. This G-geom is isomorphic to a subgroup of geoarith, as I said. And the co-kernel of that map is the Galois group we get by taking little k and adjoining all of the elements of k infinity, which are algebraic over k. Okay, so what's the benefit of this? Well, my G-geom is much easier to study generally than the geoarith. In fact, the generators for geom correspond just to the branch points of the map, which is also the case for the iterated monodromy group. So the branch points are going to be the points f to the n of c, where c is any critical point of f. In our case, we have a quadratic, so we're just going to think about the finite critical point. And we take this for every iterate, n at least one. From the topological perspective, or the standard iterated monodromy group perspective, you can see how these generators are going to act on the tree by taking actual loops in your space P1 of C minus the branch points and lift those paths to see how they act on these pre-image sets. We can also study this from a number theory perspective, which we're going to need to do when we take an arbitrary field K, because we lose the metric space structure that we had over C. In this case, we can see that we can still construct generators, but we only get to construct them up to cycle type. And the generators end up being the inertia groups of these ramified primes. I'm not going to say much more about this, but I want you to kind of take away from these ideas that we get this kind of recursive relationship between generators, and we can construct these explicitly in the topological case and up to conjugation in the number theory case. I'm going to say very little more about this, but I know the second talk today will talk a lot more about these ideas, at least the number theory perspective here. And we're going to take a kind of totally different perspective of studying these Galois groups in this work. Okay, a few more things still on these generators though, and just on the setup in general. So I have on my title slide that we were looking at post-critically finite quadratic polynomials. So we're going to consider f to be the polynomial, or a polynomial of the form z squared plus c, or we want f to specifically be post-critically finite. In general, post-critically finite means that the orbits of all of my critical points are finite, but we have a quadratic map, so we only have two critical points, 0 and infinity. It's a polynomial, so infinity is fixed. And we just in this case want to insist that the orbit of 0 is finite under our map. Okay, so now we can study the orbit of 0, and we're going to define a couple of constants, r and s. They're going to be minimal integers, or minimal non-negative numbers, so that r is strictly greater than s. S could possibly be 0, and they're going to be minimal, so that f to the s plus 1 of 0 equals f to the r plus 1 of 0. So you can see a little illustration of this, the orbit of 0 here. So if 0 is strictly pre-periodic, we have this tail of kind of length s, and then we enter our cycle. F to the s plus 1 of 0 is the first thing in our cycle, and f to the r is going to map also to f to the s plus 1 of 0. In the case that 0 is periodic, then f to the r of 0 would be 0. And we're looking at just the strict forward orbit of 0 in that case. So s equals 0 precisely corresponds to 0 being periodic. Okay. So now these generators that I mentioned on the last slide are going to correspond exactly to the elements in this forward orbit. So there are going to be r of them. Our work is going to build on previous work of Pink that does use these generators kind of carefully. So in this unpublished work from 2013, Pink, first of all, gives recursively defined elements of the automorphism group of the tree, which depend on the r and s defined on the last slide. And these are going to be conjugate to the actual generators for G-geom. He also proves a rigidity property for these generators, which kind of saves us in this case from the fact that they're only defined up to conjugation. So he proves that the group that is generated by these elements he defines is going to be isomorphic to the G-geom that we actually want to study. He also goes further and describes G-arith even more by kind of describing that algebraic extension from the short exact sequence on an earlier slide. We know that G-geom is a normal subgroup of G-arith, so he kind of constructs the normalizer of the G-geom that he constructs, and he describes this embedding of G-arith mod G-geom into this other quotient. His work is brilliant and also very kind of hard to follow, and some of it not so explicit, especially in this last step. So the motivation for our work is to kind of take a different perspective on this and try to get some different intuition and understand what's going on for these quadratic maps a little bit more. So what do we do in this work? We construct subgroups B and M of the automorphism group of the tree, which are also going to depend on the R and S defined on those slides. And we do it by constructing parity relations between the elements that we're looking at. The parity relations or the parity restrictions that we're going to give are based on algebraic relationships between the roots. So we really are using the fact that we have this Galois theory running around in the background. We can write down relationships between the roots, and the fact that the Galois group has to act in a consistent way on these elements is going to give us our parity restrictions. We also show that the B group we construct is isomorphic to the G-geom group that Pink constructs. And we show that the G-geom group that we defined on the first slide, I guess, using some of Pink's work. And we also just kind of independently show that the arithmetic Galois group has to embed in this M group that we defined, and that under certain conditions, it's isomorphic to that group. We also describe kind of exactly what this algebraic extension of little k that we get looks like, and how G-arith acts on these elements. And we give some finite conditions for when we take the preimages from a specific base point in our field, when that Galois group will be isomorphic to M. Okay. There's a lot of work that goes into these papers. They're kind of long. Our work is split into several cases, and it's split over 2 papers. So we work through different cases based on the orbit of 0. We work through the periodic case, so where S is 0 in one paper, and we work through the strictly pre-periodic cases in another paper. In this talk, what I'm going to do is kind of focus on this case, the periodic case. And then I'm going to summarize a bit what happens in this kind of standard long tail case. This is actually kind of the simplest case to understand. And then we're just kind of going to briefly mention some differences in what happens in these other 2 cases. These are kind of the most complicated ones. Okay, so how does this all work? So we're thinking now about the periodic case. Okay, so let's kind of remind ourselves of the notation here. F is going to be a quadratic polynomial of the form z squared plus c, and we've chosen r greater than 0 minimal so that f to the r of 0 is 0. So our strict forward orbit in this case looks like f to the 1 of 0, or f of 0, which maps to f squared of 0, eventually off to f to the r of 0, which in this case is 0, and then back. Okay, so this is actually the strict forward orbit of 0. Okay. Now we look for roots of unity in these backward orbits that we've constructed. There's a lot of notation on this slide. In fact, I have a lot of slides with a bit too much notation because this stuff gets a little complicated, but I want to work through examples and try to bring this down to earth a bit. So first, we have a kind of simple lemma, which says if I take any y in k bar, And then I can write the mth preimage of y, first of all, as kind of plus or minus pairs of roots. And this just comes from the fact that we're working with a polynomial of the form z squared plus c. And so every iterate is going to look like a polynomial in z squared. And that's why I get these plus or minus pairs. So now if I take half of the roots where their minus would complete the whole set of roots, and I square that, I'm getting basically a product of all of the roots up to possibly a minus sign if I'm only taking the first preimage. And so when I look at that product, I get something that looks like plus or minus the constant term of f of z, f to the m of z minus y. And so I'm going to get something like plus or minus this. So hopefully that's kind of believable. You can work through the details a little bit more if you want, just to figure out what the power on -1 is doing, but this is all kind of basic. But it gives us a lot of power. So using this fact about our quadratic polynomials, we can start to build our algebraic relationships between our preimages and specifically build roots of unity in these backward orbits. First, we have to define these kind of technical looking sets that are defined recursively. So we'll let x be any point in k bar, which is not in the forward orbit of 0. And we will first, so here's my x in my tree, we'll first look at the preimage, the first preimage of x. So that consists of some plus minus pair plus y and minus y. And I'm going to let a1 be the set containing just y, and b1 be the set containing just minus y. Now I'm going to take a preimage of a1, or an rth preimage of a1, where r was that minimal number where f to the r of 0 is 0. And I'm going to take half of the roots of that preimage, and I'm going to call that set an, and I'm going to build it specifically so that if I take plus or minus all of those elements of an, I get back the entire rth preimage. So for example, if r is 2, then I'm going to go back 2 levels above my y, and I'm going to pick that maybe this node and this node to be, right, the roots that I've assigned to these nodes to be my set A2 in this case, right? I would need, like, all 4 of them would give me my second preimage, but just these 2 is kind of what I'm looking for with this definition. And I'm going to do the same thing above B2. And I'm picking these a little bit strategically here because I want to be able to say that I can always kind of pick them in the way that I've just done. Okay, so I would keep going now. I would take these 2 A2s and I would look 2 levels back from those, and I would take half of the preimages there and half of the preimages above this node and do the same for the Bs. Okay, so what am I going to do with this? If we construct the quotient of the product of these AIs in the set A sub n divided by the product of the B's in B sub n, I claim that we get a primitive 2 to the nth root of unity. Let's call this quotient gamma n and kind of see by induction how we would prove this. So it all follows from that lemma on the previous slide. If I take this gamma n that I've defined and square it, then I'm taking maybe the product. I can split this up into maybe the product of, I should have maybe done one more level here. Sorry. If I go up to say A2 here, I said I want to take half the nodes here, none of these, half of these, and none of these. I'm running out of space. So my A3 would look like maybe this node, this one, and that one. If I take the product of these 2 nodes and square it, I end up with the thing in the square here. And if I take the product of these 2 nodes and square it, I end up with this one here. And kind of even more generally, if I take these products and split them up based on which thing in a n minus 1 they map to, I'm going to get a product over f to the r of 0 minus alpha prime, where alpha prime ranges over the elements of a sub n minus 1, using this lemma with a plus or minus sign, but I'm ignoring that because I'm doing the same thing with the betas on the bottom, and those minus signs would cancel out if they're there. This doesn't look any better yet, but remember that f to the r of 0 is 0. And now those minus signs cancel out, and I'm left with just the product of the elements of a sub n minus 1 divided by the product of the elements of the b sub n minus 1, which is gamma sub n minus 1. So if gamma sub n minus 1 was a primitive 2 to the n minus first root of unity, then its square root is going to be a primitive 2 to the nth root of unity. So this is how we kind of find this algebraic relationship that we want to look for. And this is really, even though the paper gets kind of messy, the heart of the entire argument. So the fact that we can find these relationships is what gives us these restrictions on what the Galois group can do to these roots. Okay, but to make that precise and to make sure that we're defining careful elements of our automorphism group, we need more notation, more details. So we want to define parities of tree automorphisms. And before we can do that, we first need to label our trees carefully. So we're going to label our tree. We're going to label the nodes in our tree. X naught's at the bottom, but in this labeling, it should just be the empty node. And then I'm going to label it by as I go up the tree, if I go left, I put an A, and if I go right, I put a B. So at the third level, I would have a word of length 3, which tells me if it's A, B, A, that I went left, right, left, climbing up to that point. And now we can define the parity of a tree automorphism above some node X in our tree by saying that the parity of sigma over X is 0 if sigma of XA is sigma of X and then followed by A. Notice because we have a tree automorphism, sigma of XA has to map to either sigma of XA or sigma of XB. And same thing for sigma of XB. So if we're in the case where sigma of XA maps to sigma of X followed by A, we say that this has parity 0. And if sigma of XA maps to sigma of X followed by a B, I would call that 1, parity 1. Okay, now we want to argue that we are able to label our tree in a consistent way so that some kind of chosen set of nodes gives us exactly a primitive 2 to the nth root of unity that we want. So we're kind of arguing here that we can just label this consistently. And I'm not going to give you the argument. It's an inductive argument that kind of just labels the tree as we go up. But I'm just going to tell you what the punchline is or how we want this tree to be labeled. So first what we're going to do is fix some sequence of 2 power roots of unity so that when I square zeta sub 2 to the n, I get zeta sub 2 to the n minus 1. And now I want to say that if I take the product, so this is the notation we're using for these nodes when we're in a product. So take a product over certain nodes that live above XA and some other ones that are above XB, and I'm going to argue that I get exactly we're claiming that we get exactly the 2 to the I plus first root of unity that we've fixed with this combination. Okay, so just again, to bring this down to earth a little bit, I'm going to try to give you an example of what this product of nodes actually looks like. So I'm back in the case now where R is 2. We have the set of words WRI, which are going to be the set of words of length R sub I minus 1 in our alphabet A, B that we use to label our tree. And we want S sub J to be A every time R divides J. So for example, if I'm looking at W21, I'm just taking words of length 1. And the second condition kind of doesn't come into play here because I don't have this kind of long enough. So W21 just looks like the words A and B. So what I'm doing here is I'm taking the product of XA AA with XABA, filling those in. And in the denominator, I get something similar, XBAA and XBBA. So I'm taking this quotient. If I go back to this labeling we started to make before, what I'm doing here is I'm taking really the nodes that I labeled as maybe in the set A2 as the numerator. I have X, A, and X, A, B, A. So the two that I've highlighted. So I'm kind of picking out the ones that I wanted and saying that I can label this consistently so that those specific nodes are giving me this roots of unity that I've designated. And similarly on this side, right, these two nodes in pink are the denominator. Then if I move to W22, I'm now taking words of length 3, and I want to have an A if 2 divides my index. So my second thing should be an A in this case. So this should be 4 different words, A, B, sorry, B, BAA, and BAB are the 4 words that would satisfy that condition. And when I'm looking at that, or I'm looking at an XA followed by my word, A, followed by another A. So I'd be taking exactly this node here. And you can kind of work through, I'm picking out exactly like these 4 nodes, and then on the denominator, exactly those corresponding nodes over on the B side. Okay, so all of that notation is just to kind of spell out that I'm climbing up the tree in the ways that I want to be. Right, and we're doing this consistently, not just so that my root, so this happens above my root, but I'm doing it for any node X in the tree. Okay, even more notation. I'm going to ask you to mostly just ignore a lot of the notation that's on this slide. But what we're doing in these two lines, these 2 lines of definition, is we're defining this kind of complicated element of Z2 cross of the non-zero 2-adic integers that's going to depend on all of the parities. And what I needed to do is really kind of act consistently on all of these 2 to the nth roots of unity that I just built in my tree. So this is just kind of showing me in particular, what I get from this is it's showing me the action of a sigma on these 2 to the nth roots of unity. Now I can easily construct elements of my tree that would do kind of different things to these different combinations. And I would get some kind of contradiction where I'm mapping maybe zeta sub 2 to the n to a certain power with one of my automorphisms and then to a different power with another one. And we know that those things are just not going to be part of our Galois group because our Galois group has to act nicely on these things or in the same consistent way. And so what we can do using this kind of messy definition is we can define a subgroup M of our automorphism group to be the set of automorphisms that do act consistently on the roots given these algebraic relationships that we've constructed. So we want to take the sigmas where this P sub R of sigma X is the same above any X1 as it is above X2 for any X1 and X2 in our tree. So these are just denoting any nodes of the tree at all. And then once we've done this, we can let P sub R of sigma be this common value, this P sub R of sigma X1, where X1 is any element of, or any node in the tree, any element of our backward orbits. And then I get this map PR from MR0 infinity, or this M group that we defined for our fixed R in our periodic case, into the non-zero 2-adic integers. And this is a homomorphism, and specifically what this is doing is it's telling us exactly how this sigma acts on the 2 power roots of unity. So that's how the group MR is defined. And then, so again, I'm just repeating the definition of, undo. I'm repeating the definition that I gave on that last slide here. So this is all just copied over from the last slide. And now I'm going to define this group B to be the kernel of this automorphism. So this is going to be the elements of my automorphism group of the tree that actually fix the two power roots of unity, which is what we would want in order to be part of the geometric Galois group. Okay. So the upshot of all of this is probably what you should take away if you zoned out in the last two slides. We've constructed this M so that the image of our G x naught infinity for any x naught within the automorphism group of this tree has to be contained in the group M that we defined. And if I have any element of my Galois group that fixes all of the two power roots of unity, its image has to be contained in this group B that we defined. I realize I have the wrong notation here, so this should be RS or R0 infinity. All zeros. The zeros just because remember in the case where S is 0. All right, so this works for any x naught, but specifically it works when we take our preimages of our transcendental T in this specific setup. So now, based on all of this work, we can say that the image of G arith in our set of tree automorphisms is contained in M, and the image of the geometric Galois group is contained in B, and also comparing the sizes of these groups using Pink's work. So we're using Pink's description of the sizes and our own description of the sizes of the B's and M's to see that the geometric Galois group, it has to be actually isomorphic to this group B. And based on all of the work we've done, we can see that the algebraic elements of K that actually appear in this infinite extension are exactly just the two power roots of unity, or the field generated by the two power roots of unity. And as long as zeta 4 and the square root of 2 were not in the base field K, this G arith is kind of as big as possible. It's this full group M. Okay. One more slide on the periodic case. I promise I'm almost done talking about this. The fact that we can go into and describe this G arith group also lets us go back and say even more about what happens when we take a specific base point x naught in our field. And this is using a kind of a specialization result from another paper with the same authors. And what we get is, so since we understand this group M, what we kind of get is finitely many conditions that we have to check in order to prove that our Gx naught is actually isomorphic to M R0 infinity. There's some notation on a slide that I maybe haven't fully defined, but let me go through and convince you that all of this kind of makes sense. So first, what we're kind of saying on this slide in part 3 is based on this other lemma, all I have to do is check that my Galois group over x naught up to the 2r plus first level matches my Galois group here up to the 2r plus up to the 2r plus first level. So what the notation here, MR, it should really be MR0, maybe N, is the restriction of MR0 infinity to the nth level. So as long as my image of my Galois group into this group of triautomorphisms kind of matches M at the 2r plus first level, it's going to kind of match going all the way up. And also we can check that all of this, we can check all of these conditions by kind of just checking the degree of some finite extension. What we want to know is that these DIs are kind of not already square roots in previous fields. So the upshot is we get finitely many conditions to kind of understand these infinite Galois groups. Okay. 9 minutes. I'm going to just very quickly mention that So I have all the details for this case. I'm not going to go through them all. Things are just kind of different in the different cases, and that's why they all have to be treated separately. In the long tail case, which I mentioned was the simplest case, we are going to again say we can label the tree so that certain quotients of products of pre-images always consistently give us I rather than minus I. And then we use this tree labeling to kind of construct carefully some other parity relations that we can build. And again, we're going to let n be the things that act kind of consistently on all of these copies of I that we have scattered throughout our tree. And then this consistent value of P that we get is going to kind of tell us whether sigma fixes I or maps I to minus I. So we're going to get a homomorphism from our M group into Z mod 2Z. So in this case, that's going to be the Galois group of the algebraic extension we get. We're going to see that I is kind of the only, well, our algebraic extension in this case is generated by just I. B is then going to be the kernel of this map, so all of the things that fix I. And again, our upshot is that this infinite Galois group, the image of the infinite Galois group within T, is always going to be contained in this group MRS infinity that we've defined. And anytime I have an element that actually fixes I, it has to be contained in, I did it again, BRS infinity. And so again, we get these results about the arithmetic Galois group being contained in M, the geometric one being contained in B. We could describe precisely what the algebraic extension looks like. And we already saw that we kind of, right, this P map tells us exactly how these elements of the Galois group act on, in this case, just I. And we get the same kind of specialization theorem as before. I only, in this case, have to check up to the R plus first level. And if my Galois group matches M in that case, it has to be isomorphic to M the whole way up. Just some remarks on the other cases. The other cases are kind of part of the reason the papers get so long. In the case where I have R is 3 and S is 2, besides just finding I, we get a square root of 2 showing up, and the parity restrictions that we get are even more complicated than these kind of ugly things I've already shown you. In the short tail case, we don't get I, but we do still get a square root of 2, and we get a different, again, complicated parity condition. And we also just omit the Chebyshev case from our entire argument because it would be even more complicated, and this case is already very easily described with completely other methods than what we're trying to do here. Oh, I went through all of this even quicker than I thought. So that was the end. I blew through those last couple slides thinking I was running out of time. But these are the 3 papers that I've mentioned. The first 2 are the ones covering the kind of stuff I actually talked about here, and they're the third paper that's up is talking about specializations. This is what we apply to actually to all this work to actually get the theorem that I mentioned at the end. So again, thank you to the organizers for the invitation, and thank you all for listening. And I'm happy to take any questions you have.